Let me share again. All right. So this is 4563, the second lecture. Well, actually, I guess the third lecture. And we're going to talk about the structure of the 25Z, the programmer's model, and the interrupt, the wake up issues, and how the address space is organized a little bit, and how the GPIO pins function. All right, so that's what we're going to try and get through today. All right, so here we have the random access memory. Normally, let's say somewhere in the 32 bit, the 4 gigabyte address space, this RAM is positioned, and we're not going to worry about where that is at the moment, but it's somewhere in that address space. And so we'll say this is the low address, and this is the high address of the RAM. Usually the way we set up the stack pointer is we point it to the high address plus 1 word, really, because it always addresses, the stack pointer is, it's going to push 32 bits on. When we push the return address, it's going to be a 32-bit address, so it's going to use 4 bytes. So the stack pointer, and so you always remember when we're talking about addresses on the stack pointer, we're probably going to increment it by 4 bytes every time. So the high byte, so normally we point this at the high byte plus 1. When it's going to push onto the stack, it pre-decrements the stack pointer, and so now it's pointing down here. Actually, it's pointing at the high address plus 1 minus 4, and so we have 1, 2, 3. So 1, 2, 3, 1, 2, 3, 4 different locations in RAM, and this would be the highest location. And so then we're gonna put the return address in these 4 bytes, and it'll be a 32-bit address. And every time we push, we pre-decrement. Every time we pop, we take off the address, and then we add, and then we reset the stack pointer up. If we take off 32 bits, then we're gonna add 4 to it when we're done. And so when we push, we pre-decrement. When we pop, we post increment. So the stack pointer, as you push things onto the stack, goes downward. Now, when the compiler assigns variables in the static RAM, it assigns them starting in the bottom, and it assigns the variables like this. And so the variables build up, the stack grows down, and of course you don't ever want them to meet. That's the whole point. And the amount of surveillance you have to protect you from that depends on what's going on. In the case of a compiler, the compiler should know, it knows how many variables, but it probably does not know anything about how many pushes you've had, because this is set up at compile time for a lot of the memory locations, but not all. You're also going to add some of the memory locations during runtime. But all this is runtime. So this is a dynamic event, and unless the operating system, first off, you have to be using an operating system to make this work. And if you're using bare metal code where you don't have an operating system monitoring this, then you're not going to know when these two clash. So if you run out of RAM, you may not know it, but you're certainly going to have some problems. Your variables will be corrupted, and your return addresses may very well get messed up, and you won't ever get back to where you need to get back to.
Dr. Morden?
Yeah, go ahead.
For the stack, if you have global variables, that's still runtime that those are allocated?
The globals would be established during compile time. So like I said,
yeah.
compile time variables set up and runtime variables. But when you jump to a subroutine and you pass the values, but you have variables you've created in the subroutine. Those subroutines are created in what's called the stack frame. So they only exist while that function is running. When that function returns, those variables are destroyed, unless of course you define them as static. If you define them as static, then they're preserved, but they're not going to be preserved in a stack frame. They're going to be created then down in the variable area.
Okay, and that I thought you were talking about the bottom as like the heap.
No, that's all predicated on big runtime systems and whatnot. Remember, unless you're using an RTOS, there's no OS.
Yeah, you're right.
There's no operating system. So what the code you wrote is the code that's running.
Gotcha.
And nothing else. Now there is startup code that gets everything ready and then transfers control to your program, but that startup code's not monitoring what's going on. It just initializes stuff. So there is code you didn't write, but it only runs at startup. And once you're running, it's just running your code, nothing else. Now they do have an RTOS system available, which you can use, and then it will provide some surveillance. It will compartmentalize memory and keep threads from interacting with each other and things like that. But most RTOSs are fairly limited in their supervisory powers, because you want it to be lean and mean so it can be real time. That's the problem with Windows. Windows is so bulky, it can never be real time. So you can never schedule an event to happen at a specific time in Windows. It'll never happen that way. It's going to have latency. All right.
Thank you. Yeah, that made sense.
So anyway, so this whole stack thing, generally you're going to stay out of trouble because you've got a lot more RAM than you probably will ever need. But if you put in a lot of defined variables that are, say, global and are going to exist, are going to be static, you could theoretically get in trouble with the RAM. The other thing that makes this all unpredictable is interrupts. Every time you have an interrupt, it also uses the stack, and it pushes on not just the return address, but it pushes on all the context saving for all the various registers. And so if you I forget what all is saved automatically, but I think there's a bunch of stuff that's automatically saved. Status register and the program counter. Well, the program counter, obviously, the stack pointer. There's a bunch of stuff that's saved. Maybe not the stack pointer. I don't know. But anyway, the general purpose registers, a bunch of them are automatically saved. But we're not going to program this in assembly language. We're going to program it in C, so we don't really have to worry about that. C is going to take care of all those details for us. But what it won't do is tell us if our stack runs into our variables. That it won't tell us. Okay. All right. So I wanted to cover that. Let me go back then. Shrink this down. All right. So anyway, so we have this nested vectored interrupt controller that's very powerful. It has four levels of priority, and it also has a specific the ability to put a specific address in for your interrupt service routine for every specific interrupt, and that's the vectored part. So nested means that that you can nest interrupts by priority, and vectored means that you get a specific address for every specific interrupt, a specific address for your interrupt service routine. So that's why it's called nested vectored. Okay, the other thing is there's a very nice debug module built into this chip, and it even has some micro trace buffer stuff, which I've actually never used, but it has the ability to set up lots of software breakpoints and a few hardware breakpoints, and then it can theoretically do data watch. I think the data watch basically would allow you to have it running and be monitoring certain variable values in real time. However, in order to do that, you do need a different programmer than the OpenSDA connection we're going to use. So you would need to actually buy a separate programmer to plug into it. But this programmer, this debug interface is really pretty powerful. And the nice thing about it is you don't have to specifically compile for debug. The debug is always available to you. Unlike on a low-level PIC chip, you do have to specifically compile it for debug. Okay, and then it has some advanced features with this very low latency I/O. Now, this is the documentation of this feature is god awful. It's so bad that having basically read the entire the entire manual for both the peripherals and for the ARM core, I still am fairly confused about this. It doesn't. There's no place where it spells out how to take advantage of this. But what happens is the GPIO ports are mapped to two different places in the 4 GB memory, and in one place they're the standard access, and in the other place they're the high-speed access. But beyond that, that's all the information I have. But and that's all that's in the data sheet. It doesn't really explain anything else. So why you would pick one versus the other is really never discussed in the data sheet. So I don't know. And the book that's written on this wasn't very helpful either. So, but the idea here is that you can have these, you can have this these really quick single cycle GPIO reads and writes. And they can also have a feature that's called decorated. And that feature involves using the actual address of the GPIO pin or port to have included in it some bits within the address that are not actually used for the address, but are actually used to transmit specific instructions about what to do with the bits that you're addressing. And that's called decorated stores and loads. And again, the information for how to use decorated stores and loads, good luck. It's really not in the data sheet that I've found. So I haven't really jumped into that, but there are some really nice, apparently really nice features that are available that I don't think, I'm not taking advantage of because they're so poorly documented. All right. So, and that's this single cycle IO up to 50% faster than standard IO. So in theory, if you use the high speed memory addresses, they'll work faster. But if there are any other considerations you have to keep in mind, it doesn't tell you about that. So the chip does have a two-stage pipeline, just like the PIC 16 chip does. Which does give you some advantage when you things like latency and that sort of thing, especially with interrupts. The thumb 2 instruction set, almost all instructions are 16-bit instructions. There are a few 32-bit instructions. 6 of the 56 are 32 bits. The rest are 16 bits. So this is nice because it means your code is a little more dense. The standard ARM instruction set for the M series are mostly 32-bit instructions. So that's, the instruction can take up twice the room. So that's one of the advantages of the 16-bit instructions. Even on the PIC 16, we have 14-bit instructions. So you can see, even though this is a much more complicated chip, it still has mostly 16-bit instructions. All right. So the thumb 2 instruction set is 100% compatible with the Cortex M, the M3, the M4, the M6, and there's more higher level CPUs to come. Interesting, some of these higher level CPUs use a Harvard architecture, but the M0 Plus uses a von Neumann architecture. So again, there are 56 instructions. That compares very similarly with the 49 instructions that the PIC 16 had. This has 17 registers. 13 of them are general purpose registers, again, compared with the single general purpose register we had on the PIC. And on the PIC, all our registers, well, except for the program counter, they were all roughly, 8 bits or less, whereas on this chip, all the registers are 32 bits, every single one. Now, the impact of that, if you move a byte into a 32-bit register, then you do have to worry about what happens with the upper level bytes 2, 3, and 4 when you move it into byte 1. And so there are specific assembly language instructions that will bit extend if it's a 2's complement value, or will 0 extend if it's a integer value. So that there are some considerations, because you're using 32-bit registers when you're dealing in bytes and half words, what to do with the remaining bytes in the 32-bit register. Again, it does have this linear 4 GB address space with a 32-bit address line, which is just an incredible amount of address space for the actual existing hardware you have to address. You've got 128K of flash memory. You've got, I forget whether it's 8 or 16 or 12K of RAM, but it's something like that. It's not too much. And then you have some modules in your that have control registers and data registers in them. That probably doesn't amount to more than another kilobyte or so. So all totaled, out of the 4 billion bytes, you're maybe using something like maybe, I don't know, 150,000 of them or 160,000 of them. So you can see there's a tremendous amount of this address space that's not critically needed. So what they've done then, that's why they've mapped the GPIO ports, and they've remapped them to 2 different locations, and there's a whole bunch of sort of parts of the memory that are used for other things. So it is nice that this ARM third-party ecosystem supports out there. So that's nice. Okay. What's different, of course, is this chip has Freescale modules on it. Now NXP, I guess. So that wouldn't be true for other ARM M0 plus cores based microprocessors. They would have their own peripheral modules, which would have different register addresses, names, and functionalities. So, but the nice thing is the compilers can compile into the Thumb2 instruction set, which then all the IDEs in this ecosystem could use. So again, we talk about this bit manipulation engine. This is the one that basically allows you to do these very fast single cycle stores and loads to the GPIO pins. It does have 4 channels of direct memory access, which allows your various peripheral modules to directly write or to read from memory locations without CPU intervention. And this is sort of an advanced feature that we've never really used much in this program or in this course. But certainly for a big project, that would be a very nice feature to incorporate to get better throughput. So for instance, you could have your digital to analog converter automatically reading a section of memory and writing it out, so that effectively would be a function generator for you. You could program in some random pattern of 1s and 0s, which would show up as voltage levels, and could be a random pattern generator. So there are some nice features. Let's see. So anyway, it's a very efficient chip. It can get down to very low power levels because it has extensive abilities to shut down various parts of its operation. every single module, every single GPIO port has a clock that can be turned off. And as you know, on most integrated circuits with CMOS gates, if they're not switching, the leakage currents are usually small. Now that is changing a little bit as we get into the smaller and smaller feature sizes. As you get smaller and smaller feature sizes, the percentage of your overall current use that the leakage current makes up goes up. And so with 10 nanometer technology, although this isn't a 10 nanometer chip, it may not even be a 28 nanometer chip. I'm not sure where, probably a little bit bigger than that, maybe even. But it's, as these chips get pushed lower and lower, the leakage currents are going to go up. So some of the advantages of turning off the clock to these modules might disappear. But normally, most of the power is used when it switches. All right. And this chip is just an extremely ultra low power chip. Okay, so it does have, so here it says 6 kilobytes of SRAM, and I guess that's right. For some reason, that figure seems elusive. I've seen different numbers, and now I continually am confused about it. But it does have 128K of flash. So you can write some pretty good sized programs for this chip. Again, we looked at most of this. It does have a watchdog timer. They call it a COP timer. Same idea, computer operating properly timer. And this can be set up in the same exact way. You have to turn it off before it overflows. And if it overflows, then it'll reset the chip. And that way it prevents, it gives you some prevention of a chip somewhere out in some remote device getting hung up. It'll automatically reset if it gets in some kind of infinite loop because of a power glitch or a nearby lightning strike or something like that. It has a very powerful clock module. And the really nice thing is the MCU Expresso gives you a GUI interface to make choices in this clock module. Let me see if I can pull that up. I may be able to. Let me see. Oh, I don't have an MCU Expresso up. Oh. Real quick. I'm still getting my familiarization with MCU Expresso back up to full speed. I've been so completely preoccupied with this new board we're using for Micro 2 with dual processors on it. Okay, so let me stop this share and then share it again, but to the other side. Okay, so if we let's see, so remember what you select for this. So configuration tools, clocks. So if you go to configuration tools and you select clocks and you click on this, then you get this screen here. Oh, we didn't pick a project. Okay, crap. So let me go back. So you want to go back, you hit C. This is all your choices here. So if you hit C, you go back, and then let me make sure I crank this up then. Oh, well, let's see. Okay, this should be good. Let's see what happens now if I hit the clock on this one. So there's the clock.
You also don't have a microcontroller selected either, Dr. Moore.
Yeah, I know. I thought I would have done that. It's a little hard to see the top here because of what zoom. Yeah, how come? Okay, I guess this is where it wants to set it. I don't know why that wasn't automatic. I thought it should be. So it's bubble. Okay, here. Okay, now it should be. Okay. Yeah. So now we get the clock module, and let's see. Details. Yeah. And yeah, so this lets us set it up, and there is a GUI interface here. Let's see. Well, yeah, I'm gonna have to play with this to remember. Now,
Was it like a diagram, Dr. Morton?
yeah, it gives you a diagram of the clocks coming out, and it's really.
If you go back to the clocks on the left-hand side, the left corner, it said clock diagrams. But right now you're on the pins, so you have to go back to the clocks.
Yeah, on the. You mean over here? Yeah, this one.
Yeah, and then clock diagram on the left side.
Oh, there you go. Okay,
is that it?
That's it. Yeah. So here's an entire GUI interface that shows you exactly what's going on with all the clocks. And if you look in the manual, this corresponds to the way the manual describes the clock module. And you can see it's pretty complicated. It has a phase lock loop. It also has a frequency lock loop. And here's the phase lock loop again. This is the selector, phase lock loop, a frequency lock loop. So right now this is inactive. We're using the PLL. We have an external chip. So it comes in here. It's an 8 megahertz oscillator. And I think that is exactly how it's working. I think there's an 8, I think the crystal on here is an 8 megahertz crystal. I won't be able to see it in the glasses. But anyway, so this is a the phase lock loop is set at to do 2 times 24, and so that gives us our 48 megahertz clock, and that's the master clock generator, comes out of the phase lock loop or the frequency lock loop, and that's the 48 megahertz clock. And then these are some of the other clocks that come out. This is a 32768 kilohertz. Now that 32768 has to do with that's a good real-time frequency because that's the number of seconds in a day or something. I forget. But anyway, it's easily translated, divided by powers of 2 to give you a 1 second tick. And then some of these other clocks are distributed to some of the modules. But this is the main clock, and you can change the frequency, and this clock module gives you the ability to do that. And but yeah, it's nice to see this. And then here's the tables, and this shows you what all the frequencies are, and then you can go in and you can uncheck and check these. So this is using oscillator with an external crystal, low power, and it's an 8 megahertz external oscillator, and that's what's actually soldered on the board. All right. So anyway, I'm not. So it has a lot of nice features like this, which, as your expertise, as your knowledge of the system increases and you know what you're doing, it just gives you a really fast way to make these changes. And then once you do that, then you can generate the code here by update the code. And so if you modify the configuration, you click this, and it automatically changes your software to configure the clock the way you've redone it in this interface. So that's really, really nice. Okay, so let me stop and go back to the other side. And so we'll talk more about this. There are several other really nice features, and this chip doesn't. Some of the chips have you can actually configure most of the functional modules. This one's not supported for that function, but there's enough examples that you can pretty well figure out what you need to do. All right. So, yeah. All right. And some of these, like there's this low power 1 kilohertz that's real-time clock that's set up for the real-time clock and the cop watchdog timer and a bunch of other things. You can even put 2 of your 32-bit timers to make a 64-bit timer and have a forever clock if you want. All right, so we do have, there is a 16-bit successive approximation register ADC that does have DMA support. So you can calculate results and send them straight to memory without the CPU's involvement. This ADC is very, very advanced. It can take multiple readings, like 2, 4, 8, 16, 32 readings. It can average them together before it reports a value. So it can read your ADC input 16 or 32 times, and then could do the conversions, average them together, and then give you that average signal, which is really nice. So I use that on the tilt table. We're averaging, I think, maybe even 32 readings, because we have time to take that many readings and more during a PWM cycle, because the PWM cycle is really slow. We're running it, I think, in the tilt table software, we're running it at about 10 or 12 milliseconds, but still it's spec'd at 20 milliseconds, but we're cheating on that already, running it about twice as fast, and still we have practically forever to sample the touch panel as many times as we want. So we're averaging 32 samples in the X and 32 samples in the Y direction to get to take some of the noise out of the data, which is really nice. It has a 12-bit DAC, which is nice. Again, with DMA support, and it does have a high-speed comparator. So that's the analog side. And then it has, we have 2 SPI modules, 2 I2C modules. It does have the ability to, this chip has its own ability to provide to support and be the host, the master for a USB interface, including a voltage regulator that provides 5 volts at 500 milliamps. So it's pretty cool in that regard. Then it has this low power timer. It has a system tick timer. And this is good if you're running an RTOS. This will help you do time slicing for your various threads. And then we have this, a number of GPIO pins, and there is a capacitive touch sensing module that's also built in, plus PWM and all sorts of other things. There's lots of modules. So we got PWM modules. We got this. So there's a system tick timer, and there's a periodic interrupt timer. Both of these are useful for operating systems. One is built into the actual ARM core, and one is a Freescale peripheral module. And I always get them mixed up. I can't remember which is which. But anyway, those are available, and we will use those. We use those in the in both the cup car and the tilt table software. So we've got the GPIO pins. We'll talk a little bit more about those, but they all have interrupt functionality. They can all cause interrupts with different edges, both edges, whatever. You can program these pins to operate over a nice voltage range, up to 3.6 volts. This chip, we normally run it at 3.3. So here's another breakout. So basically the same thing we've looked at, just a little bit different. And it uses this advanced high-speed bus light. So it's got a nice little bus. Remember though, so it has a 32-bit address bus. It has a 32-bit data bus. So it can move 4 bytes all at one time. And it can address anything in the 32-bit address space. So that's very powerful. It's very nice. So here the programmer's model. We have 13, which is kind of a strange number. There are 13 general purpose registers. 8 of them, 0 through 7, are called the low registers. And these are the generally available general purpose registers. So all the instructions can get to R0 through R7. Not all instructions can get to R8, 9, 10, 11, and 12, the 5 high registers. They are somewhat limited. But again, when we're writing in C, all this stuff is hidden away at a lower level of abstraction at the assembly language level, which we don't really get to play in. But that's what's going on. And the 5 high registers are used for some of these advanced instructions. It can move multiple bytes and things like that, multiple words even. So single instructions are able to actually move a whole section of a whole chunk, a number of words of memory, both loads and stores. Then there is the way the M0 plus core is set up, there are 2 different stack pointers available. But one would be for a supervisory, for like the operating system, and one would be for the applications. And so they're called the main stack pointer and the process stack pointer. Main stack pointer would be the OS level, and the process stack pointer would be application level. But when Freescale designed this chip, they chose not to implement this feature. And so there's only one stack pointer, which is register 13. All right, and there is a bit in the status and control register that selects which stack pointer you're using, which doesn't do anything on this chip. Then there's a link register, which it's somewhat inscrutable to me. I don't know. It's involved in function calls, subroutines, and things like that. But I don't know exactly what it does. And then there's a program counter. Program counter tells you the next instruction be executed. That's going to be fetched. And then there's the program status register. And this is, again, all these are 32-bit registers. This is a 32-bit register, and there's only a handful of bits even implemented in it. And it's divided up into these other parts. But they're all part of this same peripheral status register. There are some status bits on this chip. And again, C mostly hides this away from us, but there's a carry bit. There is a V bit, which tells you if you're overflowing in signed integers or 2's complement. The carry bit tells you if you're overflowing in unsigned integers. And then there's a negative bit and a 0 bit. So those are the 4 status bits. And then this primary mask, this is a way to turn off some of the interrupts and some of the exceptions. So this chip does have, if you're running an OS, it has the ability to trap for things like divide by 0 and doing non-aligned memory stores and writes, where you're trying to write a word, but it's not aligned on 0, 4, 8, or C addresses. And there's a control register then that also has to do with which stack pointer you're using if 2 were implemented, which they're not. And also it also controls in the higher level chips which assembly language instruction set you're actually executing. But in this chip, there's only one that can execute, so that bit doesn't. That bit should be always left alone. All right, this is just restating same thing. And then here's some other registers, which there's so many of these. I thought about going through these. Are just innumerable registers. Okay, so you can have up to 32 external interrupts. And each has 4 levels of priority you can set. And there's a dedicated non-maskable interrupt. There's also, you can do level and pulse sensitive interrupt lines. And then you have this very powerful wake up interrupt controller. And if you want, the vector table for what interrupt service routine is going to be executed for each interrupt can be actually moved around if you feel the need to do that. And then here's some of the debug features. Won't really spend a lot of time on this. So one of the things I want to do is talk about, I want to talk about the, so I'm going to skip through the rest of this. This is, well, I will say this. So there is a 32-bit hardware multiplier. And there is this 24-bit system tick timer. Again, the instruction set is the ARM v6m thumb instruction set. So it's usually called thumb 2 or thumb. When you incorporate the ARM core into your peripheral functionality in the Verilog file, you pick at that time whether you're going to address memory in little endian format or big endian format. And Freescale selected little endian, so it is set up as little endian. So the one really nice feature of this chip is that it really has very fixed latency interrupt handling, which means that when the interrupt occurs, you have a very you have a real guarantee of just how long it's going to take before you're in your interrupt service routine. And that is really helpful to eliminate jitter when you're sampling. And remember that if you have variable latency and there's jitter in how long it takes to get to the interrupt service routine and actually sample your input, that could result in what you're effectively doing. You're modulating your signal with your jitter, which is something you don't really want to do. So that fixed latency is really nice. Now, if you have a very slow changing signal, doesn't really matter that much. But if you're trying to push the limits and sample as fast as you can, then jitter can definitely cause nightmares for you. And then, like I said, there are these load and store multiple multi-cycle, load and store multiple and multi-cycle multiply instructions. It can be that when you get interrupted during one of these instructions, which might take a whole bunch of clock cycles to do because it's going to move maybe several bytes or several words, what they will do, they will abandon these in mid-course and then service the interrupt and then go back and restart these multi-cycle instructions without, clean it all up and restart it in a way where it works correctly and you get the right results. Just pretty challenging to do. So that's really a nice feature. Okay. You do have, especially if you implement the both stack pointers, then you have this unprivileged, privileged, different modality. But our chip doesn't implement that, so it's not an issue for us. All right. There are, I guess, so it's fairly ANSI compliant. All right. Yeah. And yeah, these are, in case you're interested, these are the 6 32-bit instructions, if you're familiar with Thumb2. All right. Here are some of the instructions. I'm not going to go through this now. What I want to do is I want to talk about the GPIO. So let me just see if I can shift to that. Yeah, no, I think it just goes back. Yeah, don't think so. Yeah, and yeah, I'm not going to do this. Okay, I think that's, well, I'll talk about this a little bit. So this is when we ran the Blink program in Code Warrior. But I want to go through this, even though we're not going to. This is not the code we're executing. We'll look at a Blink program eventually. And when we do that, I'm going to talk to you a little bit about the difference. So in MCU Expresso, it's very, very nice the way they implemented things, but they have really added some complexity. And I'll talk about this on Wednesday in more detail. But one of the things let's see, we're kind of coming up on time. So let me just go through what it takes to get these things started. Let's see. So here's what it takes to just get ready to use a GPIO pin. Okay, the first thing you have to do is you have to turn the clock on. Now in Code Warrior, we went out and we just issued this instruction. But in MCU Expresso, you're gonna use a data structure and a function and a method, a function call within a class to do this. And so it's actually more complicated, but it's the nice thing is it's every one of these, all the various things you have to do are set up in the very similar way with a method within a structure. And so it makes it it's cleaner in that regard, but it's more complicated than say it would be here. But this drives you crazy. But this is what's really going on. This is what you're actually doing when you use that method within a data structure in MCU Expresso. And we'll look at that. I'll look at that on Wednesday, show you that. And in some cases, it's actually nicer to go back and use the old methods because they're simpler. But so that's maybe. So the first thing you do is we have to turn the clock on to the port. And there's a clock for every port. Now, if you look at, so this is in the system interface module. So, and this is system clock gate control register 5. Okay, so let me just break out of this for a minute, and then I know we're getting close on time. So we'll, and I want to shrink this down, but I want to see. Here, I want to see this. So here's the actual, what is essentially the Freescale menu. No, sorry, that's MCU Express. Oh, it's not what I wanted. My bad. Here's the Freescale manual. This is the actual manual for everything except the ARM core. The ARM core separate manual. Now, this is available on Blackboard. You can also download it off the web if you don't mind looking around some. So if you go to the course here, and you go to content, and you scroll down to, I have to find them again. PDFs for hardware manuals right here. A lot of these things are hidden for you guys, but I have to, you click on this, 2 manuals. One for the KL25Z, that's everything but the ARM core, and one for the ARM core. The ARM core manual is an ARM manual. And the KL25Z, it was written by Freescale, but it's an NXP manual now. So the NXP manual is the one we're looking at, and that's what's here. Okay, so if you go down here to the system integration module, chapter 12, and you scroll down, you'll see that it lists all these system integration registers. Now, most of these we don't have to do too much with, but these system clock gate control registers, yeah, we do have to know about these. And interestingly and inexplicably, in my view, they start with system clock gate control register 4, and then there's 5, 6, and 7. There is no 1, 2, and 3, and there's no 8, 9, or 10. I don't know what that's about. But if we go to where they show up, here's what that looks like. This is system clock gate control 4. And if you look at it, you can see it has SPI 1 and SPI 0, has the comparator, has the USB, one of the USB parts in it. So if you have your own USB, if you create that on this chip and you actually have a USB that this chip is running, that's the interrupt for that, or that's the that turns that module on. Here are the clocks for the 3 UARTs. It does have 3 UARTs. It's got 2 I2Cs. So that's where these are. And then if you go to module 4, down here, there's system clock gate control, sorry, 5. System clock gate control register 5. Notice here's the bit to turn on the clock for port E. Here's the bit to turn on the clock for port D. Here's the bit to turn on the clock for port C, and so forth. So if we're going to use ports A and B to blink the RGB LED on this Freedom board, which that's how it's connected. No, I take it back. It's B and D, I guess, or maybe it's A and D. Now I forget. The tower board's a little different. So if we use tower boards, we'll have different places. Here's the low power timer, and here's the temperature touch sense module. So these are the bits you have to. So if you want to use any pin in port A and you want to configure that and use it, you have to turn the clock on for port A by setting this bit. And that's what that instruction did that we were just looking at. Okay, so so anyway, let's see, where was I? Notes. Is that it? Yeah, this is it. Okay. So this is what you're doing. You're turning on the bit for the port A mask here. Now, where does all this sim underscore SCG C5 underscore port A underscore mask come from? Well, this was the include file that was written for Code Warrior. and it's in that include file. It is not available in MCO Expresso's include file because MCO Expresso uses a class with a method within the class for this functionality. So, but it's similar, and I'll show you that on Wednesday. Then we want to set the multiplex pin for every GPIO pin has a multiplexer setting, and that goes back to the same thing. Okay, it goes back to the manual again, and if we go to that, we go down to the chapter 10, signal multiplexing and signal descriptions. So we go down here and we get to this big chart right here. The KL25C signal multiplexing and pin assignments. Now there are 4 different footprints in this family, and we are using the 80 pin low profile quad flat pack, the 80 LQFP. And so these are our pin numbers, and I'm going to show you that in just 1 second, and then I'll be done. We'll quit. So if I want to configure a pin, all the pins go by names, and they're almost all given port names. So this is PTE0, PTE1, and so forth. This is data, the power in, power out. These are the USB pins. If you create a pin, if you create if you turn on the USB module and you actually set it up for USB, those are 2 of the pins. Here's the port E pins. Here's the analog power in, analog reference high, analog reference low, the analog ground. And then here's E29, here's A's, here's another power pin, here's another ground pin, here's 18. There's a reset pin. It's actually also pin A20. And then here's pin B, pin C, a few other things. Okay, so every one of these pins generally has a name that's either GPIO related or power or ground or analog power and ground or USB related or reset. And the default setting on all these pins is either touch sensing or analog ADC or DA, or well, comparator. Yeah, comparator, ADC, or touch. And there aren't any, so the default settings are not the digital modes. So purely digital pins are disabled by default. So you have to first set this multiplexer setting to use this pin as PTE2. So if you want to port E pin 2, if you want to use that, you have to set the multiplexer setting to Alt 1 instead of the default, which is Alt 0, which in this case is nothing. And you can see the most you can have are 8. You have 8 different choices, and most of them have 1 or 2 or 3 or maybe 4. Very few of them, none of them have all 7, I don't think. Some of them have quite a few, but most of them don't. This one say PTC8, it can be comparator 0 in 2. It can be a digital IO port C pin 8. It can be the clock line for the I2C 0 module, or it can be the touch sense module channel 4. Or no, I take that. That's the timer. It can be PWM 0 channel 4. Yeah, so it's a PWM output. All right. So anyway, so you have to first set that. All right. So how do you do that? Well, that's where you. Oh shoot, that's the wrong one. Yeah, okay. All right, so here we go. So this is where you set it right here. Port A underscore pin control register 16 equals port underscore PCR underscore mux, and then you put in the multiplexer channel there. Again, this is the nomenclature back in Code Warrior days. Now we don't do this. Now we change a data structure, and we put in the setting we want, and then we call that structure with a method and use that structure with a method call, and then that sets the multiplexer pin. And I'll show you that on Wednesday. And then the other thing is, but this is what's going on in the hardware. We're actually changing that multiplexer, and that multiplexer is changed in a pin control register. Every port's got a pin control register for every pin. Even if it's not implemented, they're still there. They just don't do anything. And And then finally, we have the GPIO A pin set output register. There's a pin set, pin toggle, pin clear output register. And I'll explain those later. All right. I think I'm going to quit with this because we're running over time. All right. So on Wednesday, I'll show you how we do that in MCU Expresso using completely using data structures and methods, which is kind of the, the modern C++ way to do this. However, in some cases, it's for simple operations where one line would suffice. Now we have to set a data structure and use a couple lines, and it's a pain in the butt. So sometimes progress is backwards. But what can I say? All right. Any questions about any of that? Mostly just trying to give you kind of an overview of what's going on with this chip.
I think I found a resource, Dr. Morton, to enable that single cycle low latency input output thing. But specifically for the GPIO, I can send you the PDF if you would like. It seems like it's a compile time optimization setting that you have to put in MCU Expresso.
Oh, okay. Yeah, it doesn't surprise me that MCU Expresso would have that, because it's very well done. They have really done everything.
Yeah, I think it might have been in Code Warriors, but I never used Code Warriors before. But
no,
yeah, I just found a PDF where this FAE from NXP was, he said a whole presentation about the GPIO having a couple lines of instruction at the assembly language code, and then setting that option, it just makes it one line.
Yeah.
So.
Yeah, I'll show you what it looks like in the actual data sheet.
Okay. Yeah.
Which is just yeah.
Yeah, I couldn't find much on the data sheets, like you said, and then I had to look up specifically for the KL25Z, and then I found a PDF that's separate. It's not a data sheet; it's just the presentation that someone gave. So.
Right. Yeah. This is like secret knowledge, secret handshake. Yeah, it's terrible. It's really horrible. It's you wouldn't think a company as professional as Freescale and NXP would be doing stuff like this, but honest to God, this is the world we live in. Data sheets suck.
Yeah, they want you to come to them.
Well, yeah, they have field engineers. So for their important customers, they're at your beck and call, basically. When you order 100,000 chips or 1 million chips, they take you out to dinner, they wine you and dine you, and they will hand feed you. And so when you want to know, how do I do this? Oh, they're right there to help you. It's not published. They just have to tell you, because if the wrong people all died, this would be lost knowledge. It's awful. It's really a sort of an embarrassment. Yeah, I know. Yeah, I looked at this. I'll show you the data sheet real quick because it's kind of interesting. If I go to this chapter, let me flip that up one more time. Share screen. Yeah, so here it is. Read this in detail. I guarantee you will not see. So it's just awful. So if we go through this, so these are the registers, okay, and talks about GPIO descriptions and anyway, and then talks about all this, talks about the memory map, talks about all these pin data output register, pin set output registers, pin anyway, and here they are. Here's the GPIO memory map. So the port clear output register, port toggle, port data input, port, so it's all here, and then this describes all the fields and everything, and it's kind of interesting, and it goes through, and if we just keep going, unfortunately there's all the registers here to do, maybe. So we keep going, and then you go through, maybe we can jump over here in the, yeah. So notice we have all of them here, GPIO X, and then here we have F GPIO X. So the F GPIO X is, I guess that stands for fast GPIO input output. Never stated anywhere. Never stated. Here's the introduction of this little section. it's never stated. There it is. Does it say here, oh, by the way, these are the high-speed GPIO access points? No, it doesn't say that. And here's why you might not want to use them, and here's why you might want to use them, and here's the cost to you. I mean, it's nothing. That's it. And then this is the end of the standard GPIO right there. That's all the introduction there is. Just this letter in front of GPIO.
Yeah, that's pretty bad.
It's horrible. It's unbelievable. It's really surprising that they would do such a thing. But anyway, that's how it is. But in all fairness, MCU Expresso has been well done. So they put a lot of this intelligence into that IDE. And again, that's why we want to use that, not some third-party one. All right. We will pick this up on Wednesday, and I'll show you some of the data structures and stuff. They're all there, and it's all you can get to it all. It's just, it's complicated enough that it's going to take me several hours of playing with it just to get back up to speed when I was pretty dialed in last year. So that's how bad it is. All right, we'll see you then on Wednesday, and then we will do lab Thursday and Friday. So hopefully you can drag your carcass in and begin to play with the IDE and get a little experience with the chip, with the boards. And we'll keep looking to see if somebody gets some in stock, but so far no joy. All right, see y'all later.